Raster analyses are essential tools in GIS and should be understood by all users. Raster analyses are widespread and well developed for many reasons. In part due to the simplicity of the data structure, the ease with which continuous variables may be represented, and the long history of raster analyses. A raster data model is a regular grid cell approach to defining space. Usually, square cells are arranged in rows and columns. Raster cells store data, nominal, ordinal, or interval ratio data. Complex constructs can be built from raster data. Connected cells can be formed into networks, and related cells can be grouped into neighborhoods or regions. Map algebra is a concept introduced and developed by Dana Tomlin and Joseph Berry in the 1970s. Map algebra is a concept in which raster data layers are combined via summation and multiplication. Values are combined on a cell-by-cell basis and may be added, subtracted, multiplied, or divided. Care must be taken to avoid ambiguous combinations in the output that originate from distinct input combinations. Raster analysis is a cell-by-cell combination of raster data layers. Each number represents a value at a raster cell location. Simple operations can be applied to each number. Raster layers may be combined through operations such as addition, subtraction, and multiplication. Unary operations apply to one data layer, and binary operations apply to two data layers, and higher order operations may involve many data layers. Incompatible cell sizes and boundaries confound multi-layer raster operations. This figure illustrates ambiguities in selecting input cell values from layer 2 in combination with layer 1. Multiple full and partial cells may contribute values for an operation applied to cell A. A portion of cell B is undefined in layer 2. These ambiguities are best resolved by resampling prior to layer combination. Which layer 2 value should be used in a raster operation? Is it best to choose only the values in layer 2 from the cells with a complete overlap, or to use the median or average cell number or some weighted average? This ambiguity will arise whenever raster data sets are not aligned or have incompatible cell sizes. Raster analyses can be local, neighborhood, or global, and general analyses such as buffering and overlay may be applied using raster datasets. Neighborhood operations are particularly common in raster analyses and may be applied with a moving window approach. A moving window is swept across all cells in a data layer, typically multiplying kernel values by data found around a center cell. Window size and shape may be modified at the corners and edges of the data. A local operation is a spatial operation where the output location, area, or extent comes from operations on that same extent, as seen in this figure. A neighborhood operation is a spatial operation where the output location, area, or extent comes from operations on an area larger than and usually adjacent to the input extent. A global operation is a spatial operation where the output location, area, or extent comes from operations on the entire input area or extent. There is a broad number of functions or local operations that can be conveniently placed in one of four classes: mathematical function, Boolean or logical operations, reclassification, and multi-layer overlay. A broad array of mathematical functions may be used, limited only by the constraints of the raster data model. Raster data value and type are perhaps the most common constraints. Most raster models store one data value in a cell. Note that although many systems will let you perform these operations on any type of raster data, they often only make sense for interval and ratio data, and may return erroneous results when applied to nominal or ordinal data. There are many local functions that apply logical, also known as Boolean, operations to raster data. A logical operation typically involves the comparison of a cell to a scalar value or set of values and outputs a true or a false value. True is often represented by an output value of 1 and false by an output value of 0. There are three basic logical operations: and, or, as well as not. The and or operations require two input layers. Here we see an and Boolean operation. And requires both input values be true for the assignment of a true output. Typically, any non-zero value is considered to be true, and zeros are false. Here we see an OR operation. This cell-by-cell comparison assigns true to the output if either of the corresponding input cells is true. Note that the cells in either layer or both layers may be true for a true assignment, and null values are assigned when either of the inputs is null. Here we see a NOT operation. This operation switches true for false and false for true. Note that null input values assign null output. Logical operations may be provided that perform ordinal or equality comparisons, or that test if cell values are null. Ordinal comparisons include less than or equal to, greater than or equal to, equal, and not equal. Examples of these logical operations are shown in the slide. These operations are applied cell by cell, and the corresponding true or false output is assigned. Data can also be reclassified to select the input source based on a condition. These conditional functions have varying syntax, but typically require a condition that results in a true or false outcome. The value or source layer assigned for a true outcome is specified, as is the value or source layer assigned for a false outcome. Here, con is the conditional function. In it is a test, and that's the condition to be tested. And then next is the output if true, and that defines the values assigned if the output condition tests true. And next out if false, which defines the value assigned if the condition tests false. Note that the value that is output may be a scalar value, for example a number like 2, or the value output may come from the corresponding location in a specified raster layer, either the true layer, the layer you use if the condition is true, or the layer you use if the condition is false. The condition is applied on a cell-by-cell basis, and the output value assigned based on the results of the conditional test. A clip or extraction operation is another common type of local raster function. Source and template data layers are specified and an output data layer created. This output layer contains only the values of the source that are indicated by the template layer. The nature of the template and output data layer values depend on the specific implementation of the raster extraction. Template values are typically assigned a value of 1 for those cells that are to pass through to the output, or a 0 or null value for those that are to be ignored. Output values for the clipped area are copied from the source, while output values from outside the clipped region are typically assigned a null value. Neighborhood operations most often depend on the concept of a moving window. A window is a configuration of raster cells used to specify the input values for an operation. The window is positioned on a given location over the input raster, and an operation applied that involves the cells contained in the window. The result of the operation is usually associated with the cell at the center of the window position. The result of the operation is saved to an output layer at the center cell location. The window is then moved to be centered over the adjacent cell, and the computation is repeated. The window is swept across a raster data layer, usually from left to right in successive rows from top to bottom. At each window location, the moving window function is calculated and the result output to the new data layer. There are many neighborhood functions that use a moving window. These include simple functions such as mean, maximum, minimum, or range. Neighborhood functions may be complicated, for example, the statistical standard deviation, or they may be non-arithmetic, as the function returns a count of the number of unique values or the mode, or a Boolean occurrence. Any function that combines information from a consistently shaped group of raster cells may be implemented with a moving window. This slide shows an example of a mean or average calculation using a moving window. The function scans all 9 values in the window. It sums them and divides the sum by the number of cells in the window, thus calculating the mean cell value for the input window. The multiplication may be represented by a 3x3 grid containing the value 1/9. The mean value is then stored in an output data layer in the location corresponding to the center cell of the moving window. The window is then shifted to the right and the process repeated. When the end of a row is reached, the window is returned to the leftmost columns, shifted down 1 row, and the process repeated until all rows have been included. The moving window for many simple mathematical functions may be defined by a kernel. A kernel for a moving window function is the set of cell constants for a given window size and shape. These constants are used in a function at every moving window location. The kernel in this slide specifies a mean. As the figure shows, each cell value for the input layer at a given window position is multiplied by the corresponding kernel constant. The result is placed in the output layer. Note that when the edge of a moving window is placed on the margin of the original raster grid, we are left with at least one border row or column for which output values are undefined. There are several common methods of addressing this margin erosion. A common approach defines a different kernel for margin windows, and that's what we see here in the slide. Margin kernels are similar to main kernels, but modified as needed by the change in shape and size. The slide illustrates a 3x3 kernel for the bulk of the raster. Corner values may be determined by a 2x2, and edges can be determined by 2x3 kernels. Output from these kernels are placed in the appropriate edge cells. Raster data may also contain noise. These are values that are large or small relative to their spatial context. Noise often requires correction or smoothing. We can do that with what's known as high-pass filters. These identify spikes or pits, which can then be corrected or removed by editing. A high-pass filter returns small values when smoothly changing values, large positive values when centered on a spike, and large negative values when centered on a pit. The high-pass kernel generates a large positive value when centered on a spike. The large differences between the center cell and adjacent cell are accentuated. Conversely, a large negative value is generated when a pit is encountered. Zonal functions apply operations based on defined regions or zones within an area. Typically, the zones are recorded in a data layer with a unique identifier for each zone. A function is then applied based on the zone. Zonal functions typically require compatible cell sizes. Generally, this means the cells in the input layers and the zone defining layer have the same cell size and orientation. Note that the output here is a raster with identical values in all the cells of a given zone. This is typically how zonal functions are specified. Here we see a cost surface. The minimum cost of reaching cells in a layer from one or more source cells, you have a travel cost. For example, time to get to school or hospital, the chance of a noxious foreign weed spreading out from an introduction point. The units can be money, time, or things of that nature. The distance measure is combined with a fixed cost per unit distance to calculate a travel cost. If multiple source cells, then the lowest cost is typically placed in the output cell. A friction surface is a version of the cost surface. The cell values of a friction surface represent the cost per unit distance for crossing each cell, and it varies from cell to cell. It's used to represent areas with variable travel cost. You can add barriers, multiple paths are often not allowed, and cost and friction surfaces are always related to source cells. The center of a cell is always used in the distance calculations. Okay, and this ends our lecture portion of raster analysis.